Download this code from codegive.com, link in the description below. OK, let's dive deep into debugging openmp programs. This tutorial will cover common openmp issues, debugging strategies, and practical tools to help you identify and fix problems in your parallel code. Understanding the landscape, common openmp errors. Before we delve into debugging tools and techniques, it's crucial to understand the common pitfalls in openmp programming. Identifying potential issues early on will significantly speed up your debugging process. 1. Data races asterisk. Definition occur when multiple threads access the same memory location, and at least one of the accesses is a write, without proper synchronization. This can lead to unpredictable and incorrect results. Example why it's problematic the sum variable is shared among all threads. Multiple threads might try to read, increment, and write sum concurrently. The order in which these operations happen is non-deterministic, so the final value of sum may be incorrect. Solutions critical sections enclose the problematic code in a critical section to ensure only one thread executes it at a time. This introduces serialization and can reduce performance. Atomic operations use atomic to guarantee that read modify write operations are performed atomically. This is often more efficient than critical sections for simple operations like incrementing a counter. Reduction clauses use the reduction clause in the parallel for directive to automatically combine the results from each thread into a single variable. This is the preferred way to sum values across threads. Thread private data create a private copy of sum for each thread and then combine the results at the end. 2. Deadlocks definition occur when two or more threads are blocked indefinitely, waiting for each other to release a resource, example a lock. Example why it's problematic thread A acquires lock _A and then tries to acquire lock _B. At the same time, thread B acquires lock _B and then tries to acquire lock _A. Both threads are blocked, waiting for the other to release the lock they need, resulting in a deadlock. Solutions lock ordering establish a consistent order for acquiring locks across all threads. In the example above, if both threads always acquired lock _A before lock _B, the deadlock would be avoided. Lock timeouts use timed lock acquisition functions, if your openmp implementation provides them, to prevent threads from waiting indefinitely for a lock. Avoid unnecessary locking carefully analyze your code to see if you can reduce the number of locks you need. Sometimes, restructuring your data or algorithms can eliminate the need for certain locks. 3. Incorrect data sharing definition failing to properly specify which variables should be shared or private among threads. Example why it's problematic result is implicitly shared. Each thread modifies result, leading to a race condition and unpredictable output. The final value of result printed after the parallel region is unlikely to be meaningful. Solutions private clause make variables private to each thread. Each thread will have its own copy. First private clause similar to private, but the variable is initialized with the value it had before entering the parallel region. Shared clause explicitly declare that a variable is shared among all threads. This is the default for global variables and static variables within functions. Default, none, clause * forces you to explicitly declare the sharing attribute of every variable in the parallel region. This is a highly recommended practice to avoid accidental sharing and catch potential data race issues early on. For incorrect loop scheduling **** definition * using the wrong loop scheduling method for a parallel for loop can lead to load imbalance, where some threads do significantly more work than others. Example consider a loop where the workload for each iteration increases significantly as I increases. Why it's problematic with the default static scheduling, the loop iterations are divided into contiguous chunks and assigned to threads. If the workload per iteration is highly variable, some threads will be assigned significantly more computationally expensive iterations than others, leading to load imbalance and underutilization of some cores. Solutions Dynamic scheduling assigns iterations to threads dynamically as they become available. Threads that finish their assigned iterations quickly can pick up more work. Use the chunk_size parameter to control the granularity of task assignment. Guided scheduling similar to dynamic, but the chunk size decreases as the loop progresses. This is a good compromise between static and dynamic when the workload per iteration varies significantly but is somewhat predictable. Runtime scheduling defers the scheduling decision until runtime. The scheduling type and chunk size can be set using the openmp_schedule environment variable. This allows you to experiment with different scheduling methods without recompiling. Restructuring the loop sometimes, you can restructure the loop to make the workload per iteration more uniform, making static scheduling more efficient. This can involve reordering the iterations or breaking down complex iterations into smaller, more consistent units. 5. False sharing definition occurs when threads access different memory locations that happen to reside within the same cache line. Even though the data is logically distinct, the cache coherence protocol can cause unnecessary invalidation and refetching of cache lines, leading to performance degradation. Example why it's problematic without the padding. If data is allocated contiguously in memory, multiple elements of data are likely to fall within the same cache line. If multiple threads modify elements within the same cache line, even if they are different elements, the cache line will be invalidated and refetched repeatedly, slowing down performance. Solutions padding add padding to data structures to ensure that elements accessed by different threads are located on different cache lines. The example code above demonstrates this. Data restructuring rearrange data structures to group data accessed by the same thread together. Thread local storage use thread local storage to create private copies of data for each thread. This eliminates the need for shared access and avoids false sharing altogether. 6. Fork join overhead definition the overhead associated with creating and destroying threads, the fork and join operations, in parallel regions. If the amount of work done within a parallel region is small compared to the fork join overhead, the parallelization may actually decrease performance. Solutions minimize parallel regions consolidate multiple small parallel regions into a single larger one to reduce the number of fork join operations. No-it clause use the no-it clause on certain openmp constructs to avoid the implicit barrier at the end of the construct. This can reduce the waiting time for threads that finish early. Use with caution, as it can introduce data race issues if not used correctly. Thread affinity set thread affinity to bind threads to specific cores. This can reduce the overhead of thread migration. Use the omp_places and omp_proc_bind environment variables to control thread affinity. Tasking use openmp tasking to create more fine-grained parallelism. Tasks can be created and scheduled more efficiently than parallel regions in some cases. 2. Debugging tools and techniques. Now, let's explore the tools and strategies you can use to diagnose and fix openmp problems. 1. Traditional debuggers, GDB, LLDB, Visual Studio Debugger. Strengths familiar, widely available, provide detailed control over program execution, allow you to inspect variables, set breakpoints, step through code, and examine call stacks. Challenges with openmp debugging multi-threaded applications can be complex. Stepping through code can be tricky, as threads may execute out of order. Data races and deadlocks can be difficult to reproduce consistently. Tips for using traditional debuggers with openmp compile with debugging information use the G flag, gcc/clang, or /zi, Visual Studio, to include debugging information in your executable. Set breakpoints strategically. Place breakpoints at the beginning and end of parallel regions, before and after critical sections, and around shared variables to monitor their values. Examine thread-specific data. Use debugger commands to switch between threads and inspect their local variables and call stacks. In GDB, you can use thread_id to switch to a specific thread. Watch expressions. Set watch expressions to monitor the values of shared variables and data structures. Use conditional breakpoints. Set breakpoints that trigger only when certain conditions are met. For example, you could set a breakpoint that triggers only when a specific thread accesses a shared variable. Reduce the number of threads. Start with a small number of threads, example 2, to simplify debugging. Once you've identified the issue, you can increase the number of threads to verify the fix. Disable optimizations. Compile with optimizations disabled, example O0 or /OD, to make the code easier to debug. Optimizations can sometimes reorder instructions or eliminate variables, making it difficult to follow the program's execution. Example, GDB. 2 openbaware debuggers. Intel Inspector. A commercial tool specifically designed for detecting memory errors and thread errors, data races, deadlocks, in openmp applications. It provides detailed reports with information about the location of the error, the threads involved, and the variables that are being accessed. TotalView. Another commercial debugger that supports debugging of multi-threaded and parallel applications, including openmp. It provides features for visualizing thread activity, detecting deadlocks, and analyzing performance. Valgrind. With Valgrind. Valgrind is a free and open-source memory debugging and profiling tool. Valgrind is a Valgrind tool that detects data races and other thread synchronization errors. While not specifically openbaware, it can be helpful for identifying general threading issues. Advantages. These tools are specifically designed to understand openmp constructs and can often provide more informative error messages and visualizations than traditional debuggers. They can automatically detect data races and deadlocks, saving you time and effort. 3. Printf debugging. Description. Inserting printf statements, or equivalent logging functions, into your code to print the values of variables, track the execution flow, and identify potential problems. Strengths simple, easy to use, works in any environment. Challenges with openmp output from multiple threads can be interleaved and difficult to read. Can significantly slow down the program. Tips use thread IDs print the thread ID along with the output to distinguish between threads. Use omp_get_thread_number. Protect output with critical sections enclose printf statements in critical sections to prevent interleaved output. However, be aware that this can significantly affect the program's performance and timing. Disable buffering use flush, stout, after each printf statement to ensure that the output is written immediately. This can help to avoid lost or delayed output. Log to files redirect output to separate files for each thread to avoid interleaved output. Example For environment variables description openmp provides several environment variables that can be used to control the behavior of the openmp runtime library. These variables can be helpful for debugging and performance tuning. Common environment variables omp_number_ threads sets the number of threads to use for parallel regions. Can be useful for experimenting with different numbers of threads and observing the impact on performance. omp_schedule specifies the scheduling type and chunk size for parallel for loops. Allows you to experiment with different scheduling methods without recompiling. omp_dynamic enables or disables dynamic adjustment of the number of threads. If set to true, the openmp runtime library can adjust the number of threads dynamically based on the workload. omp_places and omp_proc_bind control thread affinity, binding threads to specific cores. These variables can be used to improve performance by reducing thread migration. omp_stack size sets the size of the stack for each thread. If you are encountering stack overflow errors, you may need to increase the stack size. omp_display_env when set to true, the openmp runtime library will print the values of the openmp environment variables at the beginning of program execution. This can be helpful for verifying that the environment variables are set correctly. Example 5 Performance profilers description profilers can help you identify performance bottlenecks in your openmp programs. They can show you which parts of the code are taking the most time to execute, and how effectively your code is utilizing the available cores. Tools Intel vTune Amplifier a commercial performance profiler that provides detailed insights into the performance of your application. It can identify hotspots, analyze thread synchronization, and provide recommendations for optimization. NuGProf a simple profiling tool that is included with GCC. It can provide basic information about the time spent in each function. Perf, Linux Performance Counters a powerful performance analysis tool that is built into the Linux kernel. It can provide detailed information about CPU usage, cache misses, and other performance metrics. Tips Identify hotspots use the profiler to identify the functions or code regions that are taking the most time to execute. Analyze thread synchronization look for excessive lock contention or thread waiting, which can indicate synchronization bottlenecks. Check for load imbalance examine the CPU utilization of each thread to see if some threads are doing significantly more work than others. Asterisk measure overhead. Asterisk determine the overhead of openmp constructs like parallel regions and critical sections. 3. Debugging workflow. Here's a recommended workflow for debugging openmp programs. 1. Reproduce the problem. Asterisk make sure you can consistently reproduce the error. This is essential for verifying your fixes. If the error is intermittent, try running the program many times or under different conditions to increase the likelihood of triggering the error. 2. Simplify the code. Asterisk create a minimal reproducible example, MRE. Strip away as much code as possible while still exhibiting the bug. This will make it easier to identify the source of the problem. 3. Check for obvious errors. Asterisk carefully review your code for common openmp errors like data races, deadlocks, and incorrect data sharing. Use the default, none, clause in parallel directives to force yourself to explicitly declare the sharing attribute of all variables. Pay attention to loop scheduling. Are you using the appropriate scheduling method for your workload? 4. Use debugging tools. Start with printf debugging to get a basic understanding of the program's execution flow. If printf debugging isn't sufficient, use a debugger, GDB, LLDB, Visual Studio Debugger, to step through the code and inspect variables. If you suspect data races or deadlocks, consider using an openmp-aware debugger like Intel Inspector or Total View. 5. Test your fix. After implementing a fix, thoroughly test the program to ensure that the error is resolved and that no new errors have been introduced. 6. Performance tuning. Once you've fixed the bugs, use a performance profiler to identify any remaining performance bottlenecks and optimize your code. 4. Advanced debugging techniques. 1. Using openmp tools interface, OMPT. OMPT is a standard interface that allows you to develop tools that can monitor and control the execution of openmp programs. This interface provides functions for tracking thread creation, synchronization, and other openmp events. OMPT is a more advanced topic but offers very powerful debugging and profiling capabilities. 2. Custom debugging libraries. You can create your own debugging libraries to track shared variable access, detect data races, and identify other threading errors. This can be particularly useful for complex openmp programs where standard debugging tools are not sufficient. Example, debugging a data race with GDB. Let's revisit the data race example from the beginning and demonstrate how to debug it using GDB. 1. Compile with debugging information. 2. Run the program in GDB. 3. Set a breakpoint. Set a breakpoint inside the loop where the data race occurs. 4. Run the program. 5. Examine thread information. When the breakpoint is hit, examine the active threads. 6. Switch between threads. Switch to a specific thread and examine the value of sum. 7. Continue execution and observe. Continue execution and switch between threads to observe how the value of sum changes. You'll notice that different threads are updating sum concurrently, leading to inconsistent results. 8. Identify the data race. The debugger output will confirm that multiple threads are simultaneously accessing and modifying the sum variable without proper synchronization. 9. Apply a fix. As shown earlier, use the reduction clause to eliminate the data race. 10. Recompile and test. Recompile the program with the fix and run it again to verify that the data race is resolved. You can remove the breakpoint and run the program without the debugger to ensure that the final result is correct. 6. Summary and best practices. Understand common openmp errors. Be familiar with data races, deadlocks, incorrect data sharing, and other potential problems. Asterisk use default, none, asterisk force yourself to explicitly declare the sharing attribute of all variables. Asterisk choose appropriate loop scheduling asterisk select the scheduling method that best matches the workload of your parallel for loops. Asterisk avoid false sharing asterisk pad data structures or use thread local storage to prevent false sharing. Asterisk minimize fork join overhead asterisk consolidate small parallel regions into larger ones. Asterisk use debugging tools asterisk leverage traditional debuggers, openmp debuggers, and printf debugging to identify and fix problems. Asterisk test thoroughly asterisk thoroughly test your code after implementing a fix to ensure that the error is resolved and that no new errors have been introduced. Asterisk use a systematic approach asterisk don't just randomly change things. Start by understanding the problem, formulating a hypothesis, and then testing your hypothesis using debugging tools. Debugging openmp programs can be challenging, but by understanding the common errors, using the appropriate debugging tools, and following a systematic approach, you can effectively identify and fix problems in your parallel code. Remember to always prioritize code correctness before focusing on performance optimization. Good luck.